Yeah, thank you very much for the nice introduction, and thanks to Fernando for this very nice invitation to this place here. So I was thinking about a motto for this conference, so maybe "Make America Cold Again" would be a good. So I will talk about a topic which came out of my work basically, but which also went into a direction which was not so much common to me before. And so it's a joint work with Victor Bangert, who is also in Freiburg, who is we have already heard, an expert on geodesics and closed geodesic and these questions. So the setup is the following, very simple. So we have a compact Riemannian manifold. So without boundary, dimension bigger than or equal to 3. So in some part, in the first part of the talk, we will maybe put as a motivation the three-dimensional case, but later we have arbitrary dimension. And we are looking at immersed surfaces, so sigma in M is an immersed surface. So I always write simply as a subset, but I mean immersed. So it's not, doesn't mean that it's embedded. There's no embeddedness discussion in this talk. And so by surface, I mean two-dimensional. So dimension of sigma is equal to 2. And then by this word, the curvature here, I mean the second fundamental form. So I'm interested in the geometric functional. I write energy of sigma is equal to, so the one normalization factor 1/2 integral of sigma, the square of the second fundamental form. So mu is the measure induced by the immersion. So it's the measure associated to the Riemannian metric, which is induced by the immersion. And A is the second fundamental form. So this is the functional A squared. And so the starting point, or the motivation, is the theorem that I proved some time ago, together with Mondino and Schigula. So this is this theorem here. So together with Mondino, Andrea Mondino and Johannes Schigula. So this was maybe 2000 and, I don't know, 12 maybe. So an existence theorem for minimizing this functional. This was the starting point. So the existence theorem goes as follows. So you assume that you have codimension 1. And you consider the special case where you want to find an immersion of the two-sphere in M. So you write S2M to be the set of smoothly immersed. Maybe I just continue here. Immersed sigma in M of the topological type S2. Smooth immersions of S2 into M. And you impose some conditions. So we want to minimize this functional in this class here. That's the goal. And so you put two conditions. Condition A is a kind of smallest condition, so you require that the energy of sigma is less than 4 pi for some surface sigma in this class. So, and the other condition is that that there exists a minimizing sequence sigma k in this class with the property that the area of the sigma k, which I simply write always like this, sigma k absolute is less than or equal to C. So these are the two assumptions. And then the claim, the result says that, this theorem says that there exists a smooth, so maybe I simply write there exists a minimizer sigma in this class of smooth inversions into M. So that was the theorem. And so in some sense, I think very satisfactory theorem. But of course, there are these assumptions A and B. So to put this a little bit into perspective, I should say that this functional integral A squared is kind of a critical function. So if you had here the energy integral A to the P with some P bigger than 2, then this theorem would be much simpler to prove. Because if you have A to the P roughly, this means that if you have a graph representation, it means the second derivatives are in LP, roughly. And if the second derivatives are in LP, by Sobolev embedding, means that you control the C1 alpha norm of this graph. And this is, of course, very helpful if you want to do something. So there is the famous theorem by Langa, the Langa compactness theorem, which, so I don't know when this was proved, maybe 84. The case when integral A to the P bigger than 2, so he has a compactness theorem for this. So in the case that P is equal to 2, it's not true that the surfaces are locally graphs or that you control the graphical description of these surfaces. So in fact, there are two approaches to this kind of theorems which have been developed in the last maybe, let's say, 20 years or something like this, or 25 years. One approach is by Leon Simon. So he still insists on describing the surfaces as graphs. So this is called under the word graphical decomposition. So of course, as I explained, this is not really true. You cannot write these surfaces as a graph. But what he does is kind of he decomposes the surface into a good set where he can control the graphical behavior, and into an exceptional set which is kind of not a graph, and tries to say that this exceptional set is in some sense small. So this is the idea of Leon Simon. So this you should here maybe write almost graphical decomposition, like to control in which way the surface fails to be a graph. This is the point here of this one. So this is the approach actually that we used when we proved this theorem here. We used Leon Simon's method to prove this theorem. So but there is another approach which is goes back to maybe, let's say, to Stefan Müller, Vladimir Schwerak, and also, of course, I should maybe mention Tatiana Toro and Hélène. So some people not to use graph representations, but to use conformal representation. So conformal representation, these guys here discovered that especially these guys here discovered that the conformal representation has a kind of estimate, a B-Lipschitz estimate, which was kind of unexpected. So it turns out that you get a nicer estimate for conformal representations than you could think, and then you can use this to apply this to existence theorems of this type. So, for example, there are many authors who did this. For example, I, together with Rainer Schätzle, proved some compactness theorems. Then there's, of course, the work by Tristan. Then there's a paper by Chen Li. So this paper is already in the Riemannian manifold. They prove some kind of Sachs-Uhlenbeck result for these kind of energies here. And then there is, again, a paper by Tristan, together with Mondino, also in the Riemannian manifold. So let me not write all the years. And there's also, I found very recently, I found there's some work in this direction by someone called Guo Dong Wei. I don't know him or her, so I don't know. So in this year, also using this conformal representation and working particularly in the direction of this theorem here. So this really relates very much to this theorem up there. So, but I don't want to go into the proof of this theorem here. It's an old theorem, but rather what I only want to do is briefly discuss these two assumptions which are made in this theorem. So I want to tell you for what are these assumptions for? How are they used? What is the role of these assumptions? And then secondly, also, how can you guarantee these assumptions? Can you check them somehow? These are the main questions where this talk is centered about. So I will start. The main focus for me in this talk will be about assumption B, but I start with a brief description on assumption A to explain you why this is necessary or sufficient or whatever. So assumption A. So obviously there is this fact that if you take the infimum in this class of immersions into M of the sphere, then this is less than or equal to 4 pi. Because you simply can take a geodesic little sphere around some point, and if you shrink the sphere, then this energy will converge just to the Euclidean energy, so integral a squared is scale invariant. So therefore this converges just to the Euclidean energy of the round sphere, and this is equal to 4 pi, or normalization. So you have that this infimum is less than or equal to 4 pi. So in this sense, this A is pushing it away from this critical level 4 pi, down below 4 pi. So there is a lemma. Maybe I show you this. So if you have a sequence of surfaces, sigma k diameter goes to 0, and let's assume here that you also have an area bound, then you can show that the lim-inf of these energies energy of sigma k is bigger than or equal to 4 pi. So in other words, you could say that this assumption A prevents the sequence, the minimizing sequence, from shrinking to a point. So A prevents shrinking. So this is the role of this assumption A. Maybe I briefly describe how this goes. So proof of this, very nice and simple. So the point is that let's assume that M is isometrically embedded into some R big N. And then you, of course, have also the second fundamental form of sigma as sitting in Rn. So this is sitting in M, but also sitting in Rn. These are the two fundamental forms. And this is just the sum. So you have the fundamental form of sigma as sitting in Rn, just decomposes of sigma sitting in M, plus second fundamental form of M sitting in Rn, restricted to the tangent bundle of sigma. So you have just this restriction. And so you see that you bound here also the second fundamental form under these assumptions here in Rn. So integral Rn sigma squared is less than or equal to energy of sigma, our energy, plus the term which comes from the second fundamental form of M. And this is just a fixed manifold, so this gives you just the constant times the areas. That the area is also bounded, so this is constant times sigma. So this is bounded in this situation here. So, but then there is a very nice monotonicity formula due to Leon-Simon telling you if you have this property here, or you have mean curvature in L2, say, then you have a quadratic area growth. So you can say that by this monotonicity formula, you have sigma intersected b rho is less than or equal to constant times rho squared. You have this quadratic area growth, and then you can argue, this is one possibility at least, that you play this game the other way around. So you take the energy of sigma in b rho, this is equal to, or let's say bigger than or equal to, the integral sigma Rn squared over sigma intersected with b rho minus a constant times energy of sigma intersected b rho. You play it this way, and you know that this is less than or equal to constant rho squared. And now if you you are in the situation of a sequence which really shrinks to a point, so let me put maybe here a k, and here also a k, and here a k, then you see if the ball here is fixed, then this will be bigger than or equal to 4 pi for k sufficiently large, just because the whole surface is contained in this ball. You can apply the Euclidean inequality. So you get that this energy is actually bigger than or equal to 4 pi minus a small constant, and this proves the result. So this is one way you can prove that. So this uses this area bound. So it prevents from shrinking. So there are certainly examples where you get non-existence. So the simple, for example, there's the following observation. So if you have sectional curvature of M negative, then you have that this infimum of the energies is actually equal to 4 pi, and you have non-existence of a minimizer. This is just by you use the Gauss equations. So the Gauss equations tell you that 1/2 a squared is equal to k sigma minus, so this is the sectional curvature of the induced metric on sigma, minus the sectional curvature of M in the direction of the tangent space of sigma. So this is also some curvature you have. And then there is some extra term, a naught squared. So if you integrate that, then you see that energy of sigma is, so this you integrate here, k sigma d mu. And now this, if the sectional curvature is negative, you have a minus sign here, then this term is positive. So this gives you strictly positive contribution. So you have inequality in this way if you drop this term. And this is always non-negative, so you can also drop that term. But then by Gauss-Bonnet, this is equal to 4 pi. So you see that you don't have existence in the case of negative sectional curvature. So there has to be some condition to prevent this phenomenon of shrinking. Yeah, this was, I guess, all I want to say about this assumption A. So you see that it's necessary to prove existence. In some sense, this is, of course, not quite sharp. I mean, but in any case, you see that this is a reasonable condition. So now, actually, there's also another role played by this assumption A that I don't want to go into too much in this. So, namely, this condition A also prevents the formation of branch points. So, in general, of course, there would be one degeneration possible, that you have a sequence of immersed surfaces, but you, for example, you develop a branch point in the limit. This is a possible scenario. For example, there is an example which you could imagine is the blowdown of the Ennepe surface, as an example, to see this. Now, I don't. You can discuss this very nicely geometrically. I don't want to go into this too much. But what you can say is that if the branch point forms, so if a branch point, let's have multiplicity m, develops, then you can say that the energy concentrates. So then energy concentrates by at least 2 pi times m minus 1. So this is, of course, just by Gauss-Bonnet. So this is a consequence of Gauss-Bonnet. Now you see that this is not quite good enough, because if you, in principle, this would allow here the formation of a branch point of order 2, multiplicity 2. So you only have 2 pi. So this is not excluded. You have energy 4 pi. But there is a lucky incidence, namely in codimension 1. And this is the only point where this codimension 1 assumption in the theorem comes in, only here. So in codimension 1, you can push this up. So in codimension 1, only the odd n are possible. So therefore, the lowest possibility is that m is equal to 3, and then 3 minus 1 is equal to 2 times 2 pi is 4 pi. And this is exactly the constant that you pose, less than 4 pi. So in this way, you can rule out this formation of branch points by this assumption. Right. I should say that this is a actually very interesting thing here, this formation of branch points. So it relates to these theorems of Helin and Müller-Schwerak very much. So there, for example, there is a theorem by Helin which goes as follows. So maybe I just quote this here, saying that if you have, for example, a sequence of surfaces in Rn, D, let's say, is the unit disk here, and you assume that they are conformally immersed, and with bounded area, and as a normalization, you assume that fk of 0 is equal to 0, so that the surface don't escape to infinity. Then you assume that the lim of the energies of these surfaces so I have to concentrate here, is less than 2 pi for n bigger than or equal to 4, and less than 4 pi for n equals to 3. And if you make this assumption, then the conclusion is then either fk converges to f, which is an immersion, and this convergence is very nice, or fk entirely converges to a constant. So you have either a collapse of the whole sequence, or you can converge again to an immersion. And this relates very much to this effect with these branch points. You see there are the same bounds here. So roughly speaking, this is really a very close relation, so very nice. Okay, now I have this was again one more, the role of A. So we have two things for A. It prevents the formation of branch points, and it prevents this shrinking, so in this theory. Now I come to assumption B. I should say how to guarantee A. So, well, to guarantee A, you just need one surface which has energy less than 4 pi. And a simple way how you can do this is by looking at the energies of these geodesic spheres. So there is an assumption, an expansion. So this goes like 4 pi minus, now comes the correction term, scalar curvature at the point P where you do this here, P times r squared plus big O of r cubed. So you see that if there is a point with positive scalar curvature, then you will be below 4 pi for small r. So in this way, this is one way to guarantee that there exists some surface which energy less than 4 pi. Of course, there could be also other, there could be also by some other reason a surface. But this is one possibility. Okay, now I come to assumption B. Which is actually the main part of this talk. So of course, assumption B is trivially necessary, right? If there exists a minimizer, then you can just repeat this minimizer as much as you want, and you have a minimizing sequence with bounded area. So there's nothing to prove. It's clearly a necessary condition for existence is this assumption B. So the question, the focus in discussing this assumption B is just how to guarantee B. So this is the focus here. So how to guarantee B. There is one simple way you can do that. namely again using the Gauss equations. So there's like an example, let's say. So if the sectional curvature of M is strictly positive, then you get B. So this is very simple, because if this is strictly positive, then you can take the minimum of this. M is a compact manifold, so this minimum is still positive. So and now you integrate here kappa times the measure of the surface. So this is less than or equal to integral over M curvature of M in the direction of T sigma d mu, just by assumption. And this is equal to, by the Gauss equations, K sigma plus A squared minus 1/2 A naught squared. So this is actually wrong what I wrote here. So this should be like this. So A naught, I shouldn't have mentioned. Maybe I did not mention this so far. So A naught is the trace-free part of this bilinear form A. So for any right? So A naught is the trace-free part. So this A naught norm is smaller than A norm. It's just a projection. So so let me see whether we can bound this. So here this is the equal to the topology. So this is just 2 pi times the Euler characteristic of sigma in general. If you have a sphere, then this is 2. But in general, 2 pi times the Euler characteristic. And now you see that this guy at least eats up 1/2 of this. So then you can estimate, for example, here simply by the energy of sigma. And this will be bounded along the minimizing sequence. So you have a result. You can say that if the of course, if you have a sectional curvature of M strictly positive, then you also have this assumption that there is one point with positive scalar curvature. This is for free. So both assumptions are satisfied. So you can have now a definite theorem. You can say that in a Riemannian manifold, dimension 3, with positive sectional curvature, there exists a minimizer which is smooth of this functional here. And this you can say. This was the state and when we proved this theorem there. But then we were a little bit unsatisfied because, I mean, we had this very small or little or weak condition here, just one point with positive scalar curvature. So this was a very weak condition, we thought. And then we have to, in this argument here, we have to put the very, very strong condition. The sectional curvature of M has to be strictly positive. So we were kind of dissatisfied and thought maybe there is a more general theorem we can prove about this area bound than this one here. And this is the outcome of this this project. So together with Bangert. So I put here 2019. I talked about this in the differential geometry seminar, so in last November in Princeton, but there I put 2018, so no, 2019. So this is more general, actually, this theorem. So let Mg, so I think also that all what I said so far is a very good motivation for this theorem, but it's maybe not the only interest in this theorem is all this variational problem. So I think that this theorem has some kind of independent interest, is my feeling at least. So let me formulate it. So let Mg be a compact Riemannian manifold. I write this down once more. So dimension is now arbitrary, bigger than or equal to 3. And also, we assume now that there exists a sequence sigma k in M of immersed surfaces. So of immersed surfaces such that the following assumptions hold. first assumption is that we always consider this sigma k with the induced metric. And with respect to this induced metric, we assume that sigma k is complete. So it doesn't have to be compact, but we assume that it's complete. So this is the first assumption. Then the second assumption is that the energy of these guys are bounded along the sequence uniformly. And the third assumption is that for the area, this is exactly not true. So the area of the sigma k goes to infinity. These are the three assumptions. And then we prove that there exists a complete, totally geodesic immersion So here also there's no assumption about, of course, the topological type of the sigma k, so this can be anything. So there exists a complete, totally geodesic immersion sigma in M. This is the conclusion, and a little extra information. So we can add that. Sigma has not the type of S2 or RP2. Yeah. Of course, RP2, we are here in the realm of immersion, so RP2 is the same as S2 basically. RP2 is covered by S2, of course. So there's no, therefore I put it in brackets. So, but we can assert that this surface does not have the type of S2 or RP2. So this last information tells you that at least this theorem covers the old theorem. Because if you have a Riemannian manifold with positive sectional curvature, then if it's totally geodesic, then the curvature of that surface is given by the curvature of the ambient. So then the curvature would be strictly positive, and this would make it either S2 or RP2. So therefore this is covered here in this theorem by this addition here that we have here. So let me make some comments about this theorem. So maybe to be short, the first comment I don't write down. So I mean, of course, you should use this as a positive result. So if the Riemannian manifold M does not carry such a totally geodesic sigma, then it means that actually we have a bound on the area of any sequence with energy bounded. So in particular, we have this assumption B. So right. So if there's no such sigma, implies that we have B. So if we add then also these conditions for A, we get an existence result. So this is one observation. Then the second point is of now when is there no such sigma? So there are some results. We did not go too much into this, but the existence of these totally geodesic surfaces is not generic. So this seems to be a kind of folklore theorem in differential geometry. We couldn't find so much good references for this. There is one reference by Bryant from 2015. So he has a little reference in his blog. So it's not a paper, but just a blog comment which he makes on this. And then there is a more recent paper which really treats this problem by Murphy and Wilhelm, so from 2018. So it seems that this paper by Murphy and Wilhelm covers mostly what we need to make this statement. except that they, for some reason that we don't know, they don't cover the case of two-dimensional surfaces in the four-dimensional ambient space. So we expect that this should be also true for two-dimensional surfaces in the four-dimensional ambient space, but their method seems to not to give this somehow for some reason. We don't know.
So what exactly is the result in this paper?
Well, this non-genericity result here. Yeah. Now, let me see. Maybe more interesting from the analytic viewpoint. There is some work of Mondino, Andrea Mondino, in Calquar 2014. So he proposes to do the following in this situation. So what you can do, of course, you can associate to the surface sigma k, you can associate the rectifiable varifold. So this is smooth surface, so you can take the rectifiable varifold, which is a measure on the Grassmannian. Now, of course, this measure goes to infinity and so on, but he rescales this simply, so you can, this is just a measure, so you can multiply by numbers, so he just rescales this by the area, so he looks at this varifold, you multiply by 1 over the measure of sigma k, and then you call this vk here. Then you have a sequence of varifolds, and by this normalization you have that this vk have equal to mass 1. And then by just very standard, weak star compactness, you get that vk converges in the sense of measures to some v, and v again has total mass 1. So this you get. Now there is a notion of second fundamental form for varifolds by Hutchinson, and this is kind of based on partial integration, where you take as test functions on the Grassmannian, so you test on the Grassmannian. And you can show that this varifold here, in the sense of Hutchinson, has actually generalized second fundamental form 0. You can show that. Now actually, this is quite general, this approach. So for this, it's not important that you consider integral a squared. So for example, this argument works also just as fine as if you take integral a to the p for some p. So this works for all p between 1 and infinity, this argument, if you want. So maybe I write here also a in LP, p between 1 and infinity, or yeah. And moreover, this argument with modifications also works if you have not a second fundamental form in LP, but if you have mean curvature in LP. You can do the same thing, basically. You just divide by this measure, and again, then you get a limit varifold, and you don't get, of course, that this is totally geodesic in this sense, but you get also you can also treat this case, and you get then that this has generalized mean curvature equal to 0. So you can do all this. Basically, it's just a functional analysis, what you're doing there. There's not much going on. The difficulty is that you don't get what you would need or what you would be interested in is some structure of these varifolds. And this seems to be not so easy to get hands-on onto the structure of these varifolds. So perhaps our theorem there would be possible to prove some structure of this varifold here, for example, that it's rectifiable. But in general, it's maybe difficult to get information on the structure. For example, in this case here, if you have mean curvature, you could take an example where you just take a triply periodic minimal surface and just scale it down. And then you get a very bad limit, which is you cannot say anything about, basically. So it's not clear how this this method kind of works. So maybe this works. This maybe I have doubts that it works. Okay, this is this approach by Mondino. But yeah. So the picture you should have for this convergence, an example basically is not really an example. So I can't draw an example of a minimizing sequence, but I can draw an example of a sequence where this energy is bounded at least. So if I have here's maybe some totally geodesic torus, totally geodesic T2, and so here's our sphere, S2. Now you can do the following. You take here on the sphere an annulus, and you wrap this annulus around the torus. So maybe here's, you wrap, and here you wrap it around. So, and now of course you can do this again. So next annulus here, you again wrap it around, and you can do this k times, right? Maybe here and here also. And then in the end, of course, you have these two caps, which are just the disks up here and down here. And you just cap this off by some surface which has bounds. So just some smooth surface, basically. Of course, I mean, you need that this is possible, so this kind of S1 here has to be bound some surface and so on, but this is just an example, so you should just view it as an example. So you cap this off, and then you see that the energy of this surface, of this sequence here, is only given by these two caps here, which is bounded. Here you have no energy because this is all totally geodesic, all this wrapping. So this would be a possibility how such a sequence could look like. Right. Now I have explained, I hope, a little bit the theorem. In the last part of the talk, I would try to go a little bit into the proof of this theorem, which is, as I said, very much different from usually what I work on, because I work on PDE usually, and there's no PDE in this whole proof. So this is just, I have to confess this. So, So the idea of this proof is a dimension reduction. So we simply do the following. I mean, we cannot control these surfaces very well. So, then we say we go to the level of curves, and we just can control, because this is one dimension lower, very well some curve. So our hope is that if the energy integral a squared is small on the surface, then we hope we find many curves where we can get control somehow. So we have to kind of put this up. So there is the first lemma, which kind of is an explicit ODE lemma, which gives you the control on these curves. So if you have, let's say here, you have a geodesic in M, so gamma of 0. So this is, I draw this as a straight line, gamma of t. So this is a geodesic in M. And now if you have a geodesic in the surface sigma, which is immersed into M, so here's the geodesic in sigma, which of course need not follow this geodesic here, because this is not on the surface. So then it could maybe go like this here. You take the same initial data, so you have here C of 0 is equal to gamma of 0, and C prime of 0 is equal to gamma prime of 0. Same initial data, and you want to kind of compare these two guys. And then there are some very simple ODE estimates. So you have, for example, that gamma prime of t, c prime of t, the distance of this is bounded by some constant e to the c, some other constant t, times integral a to t, second fundamental form of gamma of s ds, something like this. Right? I mean, this is a geodesic, so you only have the normal part along the geodesic. This is given by the second fundamental form of the surface. And also, you then, using this, you can estimate the distance of gamma of t and c of t less than or equal to b over c e to the ct minus 1, and again, then the same integral here. So you have these type of estimates that if you have compare the geodesic in sigma and in M, there are some estimates. Now there is the second, then you want to know, want to make this idea precise, that for many curves, this thing must be small somehow. This you want to prove. So how do you do this? So the way we do this is we take the unit tangent bundle. So S sigma is the unit tangent bundle. And we consider geodesics. So CV, let me write CV is the geodesic in sigma with initial vector CV prime of 0 equal to V. And then we have the following statement. So assume you have some function given on sigma. So you can imagine that this function is a squared, right? So we need this for other functions also, but you can imagine for the moment that this is a squared. And then we have consider kind of the set of bad directions for this function here. So V epsilon r of h is the set of V in the unit tangent bundle, where on the geodesic segment, this function is large. So you have integral from minus r to r h of CV of t dt, let's say, is bigger than or equal to epsilon. So this is the bad directions. So there are two parameters, epsilon bigger than 0 and r bigger than 0 is the length of this geodesic segment that you consider. And then the statement is that you get that the measure of this set V epsilon r of h is estimated. So there is an estimate c times r over epsilon times integral sigma of h. So this is an estimate. Basically, it's proved by some kind of Fubini type of argument. So you have these many geodesic segments, and it uses this proof of this uses. So L here, this is the Liouville measure on S sigma. So this is a kind of canonical measure on this unit tangent bundle, and it has the property that if you have the geodesic flow of this of the surface, then the measure is invariant under this geodesic flow, and this is used here in the proving this Fubini type argument here. So the measure is just basically just the product measure. So if you have a local trivialization of the unit tangent bundle just with orthonormal frame, then it's just the product measure. It's just the Hausdorff measure. So there's not big. So this is this bound here. So of course that's not so good, but you have to imagine that the surface sigma will be huge, right? So if you have some bound, then this is already very good because there's lots of area available. So this is very good, this estimate here. So yeah, then there is a third step. Actually, we should mention that we don't only need that there are many good geodesic segments, so where integral a squared is small, but we also need the following, that if you go here, then for most points on this curve here, again here in this direction, there are also many good geodesics, right? For most points there. So we need a kind of iteration of this thing here. So it's a little bit more complicated, but we need a kind of iteration. So for most points on this geodesic, again, many directions are good here. So we need to do this. Now, the third step is just the covering lemma. So it just says that if you have an area bound V of r, so the supremum of the area r of p, where you take the supremum over all p and sigma. So if you have this area bound, that this is less than infinity, so some uniform area bound, depending on r, of course, then you can do the following. Then for any domain G in sigma, you have the following. You have the infimum. If you take the integral of a squared on some ball, then so you take the infimum over all points P and G. Then you bound this by this function at 2r divided by the measure of G, and then times integral sigma A squared. So this is just a very simple covering lemma. So just the Vitali covering lemma. You see here that there's this, like you take the maximum number of R balls which are disjoint with midpoint in G, and then you know that the two R balls cover this and so on. So it's a very simple argument. So the point here is that of this lemma is that you get that this infimum must be quite small. If G is very big, and this is just a fixed number, then this will be very small here, this thing. So you don't only get some bound on the integral A squared, but you get balls where this is really small, this integral A squared, by this covering lemma here. Okay, and now, of course, you need this area bound there. So here's the lemma which gives you this area bound. Area bound. So it's kind of hard to get lower area bounds for these disks. They are not disks, I mean these geodesic balls, whatever they are. But upper area bound you can get, so here's the upper area bound. So you get that this is less than or equal to 2 pi times integral over sigma A squared d mu. And then here's some explicit function, hyperbolic cosine of km times r minus 1, I think, divided by km. This function here. So, so km is a lower curvature bound on m. So the km is bigger than or equal to minus km. Minus, how do I write? Maybe I'd call this kappa m here. So kappa m minus kappa m. So you need here a lower curvature bound, but this is a compact manifold, so no problem. Right, so this is an explicit bound. So this is a, of course here, I mean in this setting where you have integral A squared only, right? This, if you think about Riemannian geometry and comparison theory and so on, of course you don't have any pointwise information about these things. So you don't have any lower bound on some injectivity radius or anything. This is, you can completely forget this. So you can only use arguments which are really global in nature. So because this injectivity radius can be arbitrarily small for these surfaces, you don't bound this. So this is an estimate which really holds for all R. So this is a global argument, actually. Right. So now with these lemmas, if you have all these lemmas collected, they are basically all not difficult. You can start the proof. So start the proof. Well, you take a sequence of points, pk and sigma k, with the following properties. So what do you need? So first of all, the pk converge to some p in M. This is, of course, possible. M is compact, no problem. Then you need that the tangent spaces Tpk of sigma k converges to some plane in the 2 Grassmannian of M. Also no problem, because it's also compact. So this you can certainly do. Now you need that this does not move. Okay. Then I continue here maybe. Now you need that as a third property that the ball BRK, maybe big RK I write here, of PK, AK, I write here short, d mu k, this integral converges to 0 actually. So where the RK, the radii, go to infinity. And this you can do because of this lemma 3 with the covering lemma. So you can actually achieve that you get a sequence of balls which get bigger and bigger, but integral A squared gets smaller and smaller. So you can really do this. And finally, I don't tell you, but I say here pk good because I don't want to, this is very technical, I don't want to say too much about it, but basically it relates to this lemma 2. So I explained that on the one hand the geodesic should be nice through pk, but then also you should have this on most points on this geodesic again in the other direction should also be nice. So these properties you need there. So you need good. And now you pass to the limit and you prove the following. So lemma 5. You prove that, okay, you assume that R is not too big, so you assume that R is less than the injectivity radius of M. This is, of course, bounded, the injectivity radius of M. M is fixed, so no problem. And you also need some smallness of this R as follows. So you need that 2 pi, I forget this condition here, cosine hyperbolic, then you have this constant kappa mr minus 1 is less than epsilon naught. So and this is in our proof pi over 24. So some condition. And then the statement is that with these properties x at the point P of the ball R6 of P is totally geodesic. So now you construct with this with these properties, you construct a little totally geodesic piece, basically. So there is some, it's not easy to prove actually, so there is some problem here. Namely, if you have a point, here's P, and now if you walk along the geodesic here, let's say P of T, and so what does it mean to be totally geodesic? So if you take some vector V, which is also in E here, which is not the tangent vector, which is also in E here, right? So here's the tangent plane, maybe these two vectors, and you start in this direction, you have this geodesic here, and here in this direction you have another vector. Now if you parallel translate this vector along here in the ambient manifold, so you get the vector V of T, then of course this curve here must again be on the surface. Because this is totally geodesic, so if you have a parallel translation, you stay in the tangent bundle of the surface, then you start here, they are in the surface. So you need to prove that by the exponential mapping, you can reach this here somehow by some other geodesic. So there is something difficult here to prove. So for this, there is some triangle comparison needed, and there is this constant also here which comes in. Okay, so this is kind of the first step of this proof. Now, once you have done this, this is the main step actually, but you can still, of course, do many things. So what you can show is that this convergence here of these tangent planes intersected with BR is actually in Hausdorff distance, so you can prove a little bit of this type. And you finally, you can work at kind of I mean, the problem here is, of course, that I stated this theorem in a way where I just stated there's one immersed surface. Now, of course, in general, there could be more than one immersed surface or so in the limit. So you have a kind of structure where you have maybe many immersed surfaces and also surfaces which intersect and so on, because you don't have no maximum principle to avoid intersection of these surfaces. So what you get is like what Bangert calls a lamination structure on this manifold M, which is a totally geodesic lamination structure on M. So this you can, in the end, you can prove something of that type. So yeah, so maybe I close here, and thanks for your attention.